Yeah, the recording is on.
Yeah.
Yeah.
Okay, can I introduce Ulrich Vanderbo,
Yeah.
who is the son-in-law of Mike Manti, and I don't want to talk too much. I leave it to Ulrich to tell us a little bit about Mike, but also what are his plans for the future research.
Thank you. So, welcome to this talk about Mike and his research and the road ahead. I'll just visit error to continue.
It's always been awkward.
It's always awkward.
Try the mouse.
Yeah. Something happens. Okay. So, who were Mike Manti, actually?
He's like, ice cream break.
Okay. That's ice cream break. Yeah.
He might have done.
Oh, yeah, exactly. He would like to make fun. That's for sure. But yeah, actually, Mike, he was like educated in mathematics and especially in computer science. And he also stayed in New Mexico in the computer science department for some years before he actually went to Denmark, to the University of Aalborg. And in the 90s, he was actually a tenure associate professor there in Aalborg. And he did a lot of his, I believe, main discoveries, main research in that area. And then actually Mike, he was a very keen musician. He liked to play music and things. So he actually invented the world's first like purely digital real-time sound synthesizer around that time. So that was like quite a huge thing compared to what they have before in music. So that's one of the things he did. Then he actually retired in '98, decided to move to the mountains in Colorado, found a nice place, he built a house there, and then the reason for that was like twofold. One was to pursue like full-time research, but also to do meditation. So he was very much into like the research and meditation and the inner workings. Then he was ANPA member and president for many years as well. And then he also in '89 invented like a coin demonstration, and that's a way he used to like demonstrate how to move out of like the limitations in normal computing to something else. Then he actually held several patents, so he has patented a lot of his ideas actually over the year. And then of course he's a proud father to his only daughter Solveig, my wife. I'll just see what I can do if the mouse will find out. Okay, now it works. So, yeah. So who am I actually? Yeah, I'm like the bloke who met his daughter back in 2008. And then I, of course, got to know Mike a little bit over the years. I have always like been interested in computers since a kid. It's always been fun and interesting for me to like what you can do with those boxes in the early days. So I actually started computer science at the University of Aarhus, but I got an opportunity to join a business opportunity to become a partner in a business. So at that time I decided, okay, I can always study again. And then for many years I was like out in the business world. Then I actually, after now, having family, having 3 girls, I have been taking up programming again. A couple of years ago, I started to like talk more deeply with Mike about it and try to help him with some of the coding. And that resulted in that now I'm actually quite deep into like implementing Mike's space-like computing. Yes, this is a picture from the last visit at Mike's place in the mountains. He actually built this house, a bale straw house, in the mountains, and with the idea of having like a garden inside. So like a very big like jungle garden inside in the house. So that was like where Mike he lived for a very long time. Quite a special place, a nice place, very quiet. So you can really like feel nature and things like that. And in that place, actually outside, Mike had this bench under 2 trees outside, and that was where he was doing the sitting, his meditation, and his thinking. And actually, last summer, me and the girls stayed 5 weeks at his place, had a very good time together. But that was one of my girls, like, just filming me and Mike sitting and talking. Then, if we look into what this neural network things we are doing today is, it's not something new. It's something from, like, in the middle of the 50s, from Dartmouth or something. But from the beginning, I was talking with Mike. He always, like, emphasized that in his belief, like, neural network was basically flawed. There was something wrong with it, basically. So that's why he was like looking into what can we do instead of just doing like what everybody else is doing, neural networks today. And why is something flawed, or what is actually the first way you will notice something is flawed? That could be that, like the case with OpenAI, they start hiring a lot of lawyers. Then maybe you should be a little bit aware that maybe there's something not completely just working by itself. So actually, yeah, a lot of lawyers is apparently being hired and paid to help OpenAI figuring out the problems they seem to have in some areas with this new technology, especially the large language models they are introducing to the world and a lot of people and companies are using today. So that you should be a little bit skeptical. Something is maybe not perfect. A different thing I find quite interesting is a recent paper actually from Stanford and Rice. That is that some scientists, they've tried to investigate that if you have a neural network, especially if you have these long, big language models, then the way it works today, that is like if you have this ChatGPT and thing, it's basically trained more or less on all the information we have today on the internet. So you're taking a network and you're training and you're training and you're training with all the knowledge we humans have created out on the internet. And that's what we're using today, and that apparently works for many things. Sometimes it's a little bit biased and whatever. But then we are also today using those large language models to produce new contents. So they are producing, papers for us, and they are producing images and things like that. And that goes out on the internet. And then we have new models that's trained on something that's partly made by humans, but also made by machine. And they actually investigated, and it's quite interesting paper, this one, what happens when the amount of information you're training on starts to become more and more from other machines. So when you're training machines on the output from other machines, what happens? It seems like in some cases very few repetitions, like 5 times, then what you're putting in and training, it gives something totally crazy. So the more you're training a network, a neural network, a big neural network, with content that's generated from other intelligent machines, something strange happens. It actually, it breaks down. basically. So the more the machines are consuming things machines have made, the worse it gets.
It's like machine incest.
Yeah, use inbred. They are comparing it to mad cow disease, basically. So now we have lawyers, and we have, in some cases, neural networks, and especially the big models. We should be a little bit suspicious that maybe not everything is good.
Several years ago, it was rubbish in, rubbish out.
Yes. So garbage in, garbage out, basically. That means that actually very early on in the 80s, Mikey realized that something different was needed. We should think in a different way when we are thinking intelligent machines. And that's what he had been thinking about for a long time. Here I'm trying to compare what we are doing today with neural networks and Mike's idea about what we could do. I want to emphasize that just because this is red and this is blue, it's not like this is totally bad and this is totally good. In my opinion, what we are doing with neural networks today, it has a place in the world, but it definitely don't have a place in the big language models and things like that. So, in my opinion, if you use a smaller neural network for some simple tasks, very constrained tasks, it's a nice tool and it works and it's not too difficult to train and things like that. But if you try to scale it up and make it like thinking like a human or whatever, we're going into problems. But basically, what we're doing today, that is, we are taking a network of, and then we are throwing in informations and we are adjusting some weights. That's what we're doing today. And in my opinion, it's a kind of an advanced comparing machine or a copy machine. So that's what we have today. What Mikey was thinking about, that is a way that we can have a machine that can actually generate information more or less by itself, and where it don't need to be trained a lot all the time. So that's like a huge distinction. So it's more like, how can we make a machine that can act like a child being born, who knows nothing, starts interacting with the world, and then it learns within that interaction and grows up and it becomes something. That's more the thinking. If we do that, then there are some nice, interesting things. And that is, today we have difficulties, and that's probably why the lawyers. Nobody can tell how the decisions is made in a neural network today. It's like a black box. You put something in, and it says, oh yeah, it's a cat or it's a dog. But you cannot ask it, why is it a cat? You can't see it. Even the programmers can't go in and find out. So we have these issues with biases, especially when you start to using this as profiling people, maybe being bad guys or less bad guys or good guys, and even judges are sometimes getting help from machines and black bias and different things. So a different way, that is, Mikey was thinking about generating information by co-occurrences of things. And if we do that, then we actually have a way where we can go back. So that means that it supports transparency, so we can actually go back in the system and see how it reached this conclusion. Neural networks needs a lot of data to train. What Mike was thinking was more like a child growing up, few repetitions will very fast learn something. Neural networks, it's only one way. You're feeding in information, goes through a network, and a result coming out. In Mike's way of thinking, it's more like wave-like. Something goes in and comes down. I'll get back to that. What we have today is what I'll say is like narrow artificial intelligence. It's good for very small tasks, but you cannot, as I know it, scale it up and make it like a general artificial entity. what Mike is suggesting is actually something that would be able to learn everything, whatever it's trained on. So it'd be more general entity. And then neural networks, it has like a fixed amount of input layer. If you train a network, then you cannot say, now I'll want 500 extra sensors and throw in. Then you have to start over and train again. In my system, it's more flexible. You can adjust the amount of input to the system, and it will react to it. And so basically, with Mike's work, it's more like time-like what we are doing today. And Mike's suggestion is that we should move to something that's more space-like. So the big question is, if we should do that and make it work, how do we generate information instead of consuming it? Because if we are thinking time-like as we're doing today, then in computing we have one step, next step, and third step. And that means if we have 3 plus 4 equals 7, then at the moment we have the result 7. The computer cannot tell how we reached that result. It just did something. So we need to move to a place where we can actually tell how we got some result and where it came from. And that was something Mikey was thinking a lot about. And then actually, back in the 80s, he came up with an idea. It's called the coin demonstration. He has probably been showing it to people many times, but I will try and go through it again. So basically what it says, that is that I think I have 2 coins. I actually think it's Mike's coins, just to make it fun. But that means if I take my hands behind and I put one hand and show you one coin, then I close it and remove it again. And then a moment later, I'll put forward a hand and show you one coin. And then I'll close it again. And then I will ask you, how many coins do I have? What will you suggest will be the answer?
At least 1.
So, at least 1, yes. So, could we agree that it could be 1 or more than 1? Yeah. So I have 1 or more than 1, right? Then the issue is, how do we decide this? So what happens when you can answer this question, how many coins I have? So 1 or more than 1, that's the 2 possibilities. But you need to receive 1 bit of information before you can decide if it's 1 or more than 1. So now I'm actually showing you that I have 2 coins now in my hands. So now you can give me an answer. You can actually tell me how many coins. And you can say more than 1. But how does that happen? The interesting part Mikey was very interested in, that's actually where did that information came from?
From behind your back.
Yeah, from behind my back, yeah, we could say that, but how could you actually now answer the question? And Mike, he believed that it's the simultaneous presence of the 2 coins, that they're now present, the 2 coins, at the same time. That gives you 1 bit of information. So that means that just the co-occurrence of the 2 coins have given you 1 bit of information. And that's quite interesting when you start thinking about it. Because that means actually that if you're thinking in co-occurrences, and there's information in a co-occurrence, then you're actually in a world you cannot reach sequentially. And that means when you're talking computers, now we're outside of the limitation of Turing's world, Turing's box, whatever you call it. So just remember there's information in a co-occurrence. And that's the same again. The co-occurrence gives us information. So just the simultaneous presence of something, the gift is actually making information. So we're a long way from traditional Boolean algebra in this area. Then I would like to try to explain a little bit more, because what Mikey has been doing, he has built all this together. He tried to do some mathematics and how we could do some thoughts about implementing it, and he's calling it all space-like computing, and he has patented that part as well. But that means that now we can actually do something else compared to a neural network. If we have two places, A and B, two platforms, and we have a sensor A with a plus and minus, and that'll be empty platform or something on the platform, right? We have the same over here. So we have two platforms, we have two sensors. Then we can actually look for a co-occurrence. So if we have a system that's looking for A plus and B minus, that means that A is filled and B is empty. When that happens, we actually receive a bit of information. And what we receive, or we can at least build with computers, that is, we can say that this co-occurrency of these two states, that's an impulse. That could be an impulse to empty A and fill B. So we have a co-occurrency, and then in Mike's world, that co-occurrency is an impulse, and that impulse is actually bubbling up in the hierarchy. And when it reaches the top, it's changed to a goal, and then it triples down. And on the way down, it looks for a plan to do this in the system. This is a very simple example. Then it becomes, or it touches an effector, and this effector is basically changing these two at the same time. So it empties A and fills B. And now we have moved the box from A to B. The very interesting part, in my opinion, is, so if we're looking to what happens, that is, what did we do? We have a system with two sensors, and in these two sensors, like a confined small world, as soon as we sense this co-occurrency, A filled, B empty, it automatically gives us some information. We are creating information we can use to look for plans to move A from B. And that's critical, because if we're thinking that way, then just by having a lot of sensing capabilities, just like our brain has, then our brain could actually internally, or the system will internally build something just based on the sensory input, and it will decide what to do. So we don't need to train the system like neural networks. Of course, it won't work just with two sensors like this, but you can combine in each levels. You can have more than one co-occurrency happen, and you can have meta sensors detecting co-occurrences of co-occurrences, and so on. And that's very interesting, because then we actually can say in a system like that, if we build it, then learning is actually patterns of synchronization. So the patterns that's built depending on the co-occurrences we are receiving and detecting from the sensory interface. So I find that very interesting. But one thing is finding something interesting. A different thing is, of course, like, will it work? Were Mike actually on the right track? Is it worth to do something about this? Mike, he left a paper that's not published, and it will come here in ANPA latest next year, where he is like looking a lot into a mathematical model about explaining all this, what's happening in this hierarchy of co-occurrences and co-exclusions and so on. So he used a lot of time to make a huge mathematical explanation and reasoning about that. That's not my strong side. So I hope you will help and see what works and what won't work. In this mathematical model, he actually found these following forms. So he was, besides just thinking about how to build intelligent machine, my impression was he was thinking a lot about how the universe works, quantum mechanics, all the things he could actually research into. So I find that interesting, but I can't validate his thinking. I can't follow it, so I don't know if there's something there or not that's really interesting, but I hope that you will help with that. So why I believe that Mike was actually on the right track. What we see today in neuroscience, or actually for many years, that's the discovery that the cortex of the brain is built of similar area units, and they're calling them cortical columns. So it seems like the brain is one column, and then 150,000 of them that builds our whole cortex, the outer part of our brain, where we believe everything is happening. So that's from neuroscience today. Then it's believed that one cortical column like this, since it's replicable, nature have it with replicating stuff, that it probably is doing the same thing. So maybe there's one kind of universal algorithm or some basic algorithm, if you're looking with computing, that's happening inside one cortical column. So that could be interesting to investigate. There is a guy here, he actually made the Palm Pilot, I think, to begin with, the small, very first nice handheld computer. He has been very interested in how the brain functions, and he has started the Red Book Neuroscience Institute, where they have a lot of researchers and thinkers about how is the brain working, and they're trying to prove what they can prove about it. And they came up with the idea that the brain actually builds reference frames. And that means the brain is inside our skull. It's not connected to the world, but it's connected, it can see and it can hear and do stuff. But how does our brain know that if I'm touching my hand, or if this is my phone, where my phone are, so I can actually grab it and move it around? That's they were thinking a lot about that, and they came up with the concept of reference frames. So somehow to build reference frames or maps and things, so the brain understand, okay, there's my cup, there's my phone, I'm going in this direction, or so the things are shifting. So the brain, due to their research, is updating reference frames all the times. And I have a little bit feeling that reference frames, it looks quite like if you have patterns of synchronization, if you build this co-exclusion and co-occurrences hierarchy Mike is talking about. So some patterns mimicking the world, and maybe that's how it works in the brain. then I was also thinking, yeah, but maybe there's more just to it. And so I also, sorry? Okay. I also think that we can just think of nature. It seems to me, at least, that nature is concurrent. And then there is new research that suggests that our brain uses quantum computation. And actually today, John here actually also suggested that that's true, so I'll just take that as evidence. So let's say the brain is using quantum, right? Then if you have a child and you show them cats and dogs, they would quite fast learn what is a cat and what is a dog. You don't need to show them 10,000 pictures just to have a chance of guessing a little bit correctly. And if you think about it also, I think the brain is much more energy efficient compared to the computing systems we're building today. So that also gives my impression that maybe there's something that's interesting to work with. So if we buy into that, yeah, it would be interesting to do what Mikey was thinking, and that could probably be an interesting way to do something. Then how do we build it? We need three things. We need some programming language or paradigm that we can start building it with. We need to think about how can we implement this, like two things happens at the same time, this currency or co-exclusion. And on top of that, we need to think about how can we make a forever running piracy that's continuously reacting to the world. So that's like the main challenges. The first one, what programming language or paradigm? I have chosen the language called Erlang. And it's because that Erlang actually reflects how things happen in the real world. It has a built-in support for massive concurrency. It's built of a lot of small processes, individual small processes, or thread, if you like, that concurrently is working. And they are interacting with each other by message parsing in this programming language. It's actually used in telecoms, banking, and also like WhatsApp. So when people are using WhatsApp, since you have so many people communicating and things at the same time, things happening at the same time, then Erlang is very good for it. It's a functional programming language, and it has built-in the possibility to forever running loops. That's just a basic property of this language.
Can I ask people to mute themselves before discussion? Because we have some people.
You need to mute, Dot. So then the second thing is that how do we actually represent and detect this co-occurrency thing if it's difficult to do in traditional computing memory? Yeah, it's one that's talking, but yeah. So basically what we need, that's a kind of information sharing system where things can happen concurrently. For a fire complex.
Can you please mute yourself for the next 5 minutes?
Yep. So the concept, Doc, can you hear me?
Yes.
Yes,
I can hear you.
Okay, perfect. Can you please mute yourself and then after the presentation ask questions? Thank you. So we need something different that the computing memory have today. Luckily, somebody already invented it. Very nice, good idea. Came out of MIT in the 80s. And it's called a tuple space. So somebody already invented it, but it hadn't really got mainstream in computing. What's interesting with this tuple space is that when you're looking for something, you're addressing it associative. instead of just by address to receive something. Then this tuple space, it has a range of operations. So the original implementation, it has like out, in, read, and some predicate of those, and eval. That can do something. We'll come back to it in a moment. But Mike's idea, what they always was playing around but had trouble implementing in C back in the 90s, that was to add some extra functionality to this tuple space concept already invented. And that was like the detection for co-occurrences and co-exclusions and so on. So what is a tuple space, if we should try and explain it quite easily? It's a blackboard metaphor. So it's basically what we see around here, that's different processes, individual processes, and that could be an airline not knowing each other, right? If they want to communicate things, then we have one program over here. It reads its program, and then it have an instruction saying, oh, out. That means throw out this tuple into tuple space. So this process, it builds this. So now in tuple space, there's invoice 2,500 Great British pound, right? Tuple. Okay, and it succeeded. Then we can have over here, I will say, yeah, in the tuple space, there can be already a lot of tuples. So everybody can come and put something on the blackboard, or they can take something from the blackboard. They don't need to know each other. They don't need to be present at the same times and things like that. So that means if this one is coming in its code and it goes to an instruction that says, oh, is there a co-occurrency of two tuples, tuple A and tuple B, in tuple space? It looks in tuple space, and yes, there were two. And then it's allowed to continue in its code, right? Then there is a process down here. It's read, so it's looking in tuple space for a goat, the value of goat. But there's no goats in tuple space. So what happens is actually now it's blocked. So this process in its computer instructions, it's blocked. It's not allowed to continue doing whatever it's doing before it shows up a goat out in tuple space. Maybe never, we don't know. So it's blocked. And that's the same down here. This one, the co-occurrency, the interesting part is it's not just two tuples. It can be any amount or number of tuples it's looking for. So it can be 1,000 different tuples. When all is present at the same time, it's allowed to continue. But since we are missing a C, there's no C in tuple space, this one is blocked as well. This one, it asks tuple space like in. It's looking in tuple space for something. It looks for an invoice, and it looks for Great British pound, and then a question mark. And that's the associative search that's coming in. That means, okay, look in tuple space, find a tuple of 3 elements, where it's first is invoice, the last is Great British pound, and we don't care what the middle is. And it looks in, oh, there are 2 of those, but it takes just one of them, and deletes it in tuple space and gives it to this process, and it continues doing stuff. So that's the basic mechanism of a tuple space. So what is it good for? Basically, it solves a lot of problems that people are doing in very hard ways today, actually, in computing, instead of doing it simple and easy. You can easily coordinate parallel computing, like master-worker tasks. You can do process coordination between processes. You can do synchronization through the tuple space. You could use it as distributed data structure. You can build your arrays. You can build lists out there. You can build whole mathematical structures. You decide how they are. Throw them out in tuple space and rank on it. It can be used as a database system if you want, basically, and a lot more depending on how you're implementing this tuple space concept. So that's a very interesting thing. And I've been implementing quite a lot of this in code. This is in airline. Small example. I'm now compiling the program in airline. That's what happens. Then I start. I'm calling it an info-register space instead of a tuple space. That space is now created. Now I'm starting a test process, a separate test process, which job is just to populate tuple space with, in this case, 100,000 random tuples, just to fill something in. So now I'm filling in 100,000 tuples in this tuple space, and it takes half a second for 100,000, but just boom. Now I'm starting a process, one single process with a job asking for when is A and B present in tuple space, like the co-occurrence of A and B. I made 10 of those. So now we have 10 processes all around the tuple space, independently, concurrently, doing stuff. And now I throw out an A, a tuple A, to tuple space. And I also throw out a tuple B to tuple space. And in that instant moment, all those processes are actually notified at the same time in the tuple space. And they can continue doing whatever they're supposed to do. So what takes longest time is actually to write this text to this terminal. So that's some of the things the tuple space can do. So it ends actually up as like a kind of coordinating language for computers. You can use the tuple space for, and that's an important part. Then the next part is how do we like build this forever running hierarchy to connect to an array of sensors outside to the world and to react, like detect co-occurrences, and by that detection generate information and acting on that information. That's very interesting. Yeah. And that is like, one way is of course focus on looking into the details of this algebraic model Mikey is like suggesting for this whole things. I really much would like people to look into that and let me know that are there some issues there, what can we do there, are there something where this is definitely not possible in a mathematical sense or physical sense, right? Because then maybe I can adjust what I do in code. So that would be really interesting if people do that. Then this tuple space I just showed you, it's running in RAM on computer, so it's running very fast. It needs to be fast. If it's not fast, then you'll end up with a very slow computer and it doesn't matter. And then we use this airline language because the built-in process system and the forever running loops. And then we can build actually what Mikey has patented. So what is the road ahead? I have already implemented most of this extended tuple space concept in airline, which I call an info-register space. I like coffee, and it's something with information, so instead of bar register, it became info-register, right? So then, when that part is finished, we need to build and test this space-like computing hierarchy. That's actually only not so many processes running concurrently on top of this, and then we can start playing around with it. Then the obvious things that's always very difficult and easy to say, that is introduce the system to the world, use the system to do good stuff, fight against misuse of AI generally. Space-like computing is patented, and so of course try to protect that way, and then even try to use a good AI to fight off bad AI, because that's probably what we need in the future. We can see it already today. Some people are actually programming good neural networks to detect when neural networks are making like fake images and things like that. So there is like a race going on. Then this is not public yet, but it's a closed website, but that's like the main idea. That is to work on development this new kind of AI, introduce that to the world, and use it to actually do some good stuff. And that means explicitly not do bad things like war, advertising, surveillance, gambling, and whatever. So keep in mind to do something good, even though it will be very fast and much easier to earn money that way. But we don't have to avoid that. This is some of the documentation for this API, this InfoVista space I'm building with a lot of functionality in. So I'm working on this. So I'm in this place where, when I have the time, I work on my computer and let's see if it works or not. I'm sure all this I can make work. I have all the technical things is already thought out and it works. Maybe I'll have some challenges understanding the whole hierarchy and the running concept in the mathematic parts. Luckily, Mike did quite a lot of pseudocode how it should work. So I think all the things I have learned from Mike, his last papers, but actually also his papers from the 90s, I have all the information to actually go build a new kind of artificial intelligence, real general intelligence that can learn anything and grows up like a kid. But it's just like slow evolving, just like a child. You have to learn it and interact. But it will be able to do anything. And I think that's like the holy grail in artificial intelligence, if you can do that. But I think it's possible. With that, I will actually, while reading all the things from Mike, I will end this presentation with a word from Mike from 1978. I'll just try and see if I can move this one a little bit. Yeah. What Mike says, and I think these words says a lot about Mike, who he was and how he was thinking. But there's also some wisdom in it, if you like. So Mike says that the word purpose implies the existence of some particular outcome, an ultimate result, and as such is implicitly sequential notation. Systems like nature are not sequential, do not explicitly produce any particular outcome, and hence have no ultimate purpose. The burden on us as spiritual beings is to find it within ourselves and not fall off the responsibility on a system which will destroy us if we fail. So that's the last word from Mike. Thank you.
Thank you.
Yeah.
Can I ask Mike Palmer, because I saw him raise his hand. Mike, do you still want to ask something or comment?
Yes. I work very closely with Mike, and one day I was sitting next to him when the guy who wrote his obituary, which is published, David McGovern, came up with a very simple idea, which is roughly the same as the 2 coins. If John Rowlandson is in the audience, I ask him to take a piece of paper, which is roughly square, fold it in half twice, and then tear the inner corner. And out of the piece of the original piece of paper, if he's done it roughly, there's like a diamond. And this is not the opposite of the original paper. It's Mike's way of saying there's one bit of difference in a physical reality situation. I was very impressed with that, and I kept a piece of paper with the little piece ripped out in my wallet for 10 or 15 years, and whenever I took it out, I remembered Mike Manfi.
Yeah, thank
you.
Okay. Any questions from the audience here? I have to say that we are melting.
Yeah, we're melting. It's very hot inside, that's right. Yeah.
So, okay.
Yeah.
You use the word tuckle.
Yeah.
Is that linked to Cartesian products?
No, it's in my world. It's just some piece of data. You decide whatever it is.
Okay.
So the tuple, it's just like, it's not a list where you can have unlimited element. It's a fixed length tuple. So that you decide when you're making it if it should contain 3 elements or 100 elements.
So it's a flexible structure.
Yeah, it's a structure where you decide if it should contain 3 or 100, right, to begin with. And it can include in the places in the tuple, you can throw in like lists, strings, integers, whatever. So you can like store everything in tuples, and that's why it's clever. You can use it to a different way of doing storage in a computer.
Yeah.
I love this. When we talked about it over breakfast at some stage, because you're Danish, I didn't hear tuple, I heard tuple.
Yeah.
And I thought that was a lovely thing because it's an idea of a space that things can fall into or fall out of, and you can produce things which then initiate a stream of events that come from something that's looking at like a picture of the like a copy of something like the real world that we're looking at the moment. You have something that has a set of things and that reacts, and you have a rubbish comes in, you do something. Things happen, and the kind of structure you have there looks to me like a much closer thing to reality than the way these things are normally done.
Yeah.
Because you can have a very large number of things that are looking into this space, and the space can have a very large number of different kinds of objects which come into it. And check on it. It's very beautiful.
Yeah.
I can see that Doug has raised hand.
Yes. What do you say, Doug?
Hey, I have a question. I think you and I have talked about this, Ulrich, that the tuple space, you're still doing a matching, right? You're doing a search in the tuple space for things.
Yes, that's correct.
The match. And you care to comment about whether or not that scales?
It scales. Let's say the search in tuple space happens in constant time, or near constant time, no matter the amount. So even like 100 millions of tuples, it's nearly instant searched.
Is this because it's using some kind of hashing algorithm or something?
I'll say as much as I built the basic structure with key value tables. So that's as much as I would like to say right now. But yeah, I have figured a way around doing extremely fast search, like associative search in the tuple space, and that's like a very, very important thing. Because if you are very fast at throwing things out and things, but if it takes forever, to retrieve things and find things and do stuff, then it will get slow. But Erlang has the concept of Erlang term storage. It's a kind of table you can build in memory in Erlang, and it is actually built so it is accessible concurrently from all the different processes running in Erlang. So it's a very interesting data structure you can work with. So you can, in many situations, you can actually scale it up easily.
Yeah. Okay. So, I mean, because I worked on neural computing stuff too, and we were doing associative style memory. I mean, essentially Hawking is working on Canerva memories. Canerva memories are content addressable memory, and the way you find something that's near it is that you find essentially things that are near it in the space. But in order to do that, you have to actually have a high dimensional version of radar that doesn't scale with an infinite number of dimensions. So, and so even though it seems like a nice idea mathematically, its implementation does not scale. I mean, you can put a lot of concurrency on it, but somehow the quote brain/mind scales where where these other systems don't necessarily scale. So.
I totally agree, and I think it's a very interesting engineering problem.
Yeah, it is.
Actually, I did a little bit math this morning back at home, just because if we are looking into the knowledge of actually a human brain, how big it is and connections and things like that, people says that it's about 86 million neurons in the brain. I was trying to calculate back, okay, how much memory RAM do we actually need to have in this airline system to do that? And it turned out if you take around 400 computers, each having 100 gigabyte of RAM, then you can actually simulate, then you can handle the amount of neurons you have in the brain in airline. And luckily, airline is actually made so it works in distributed, that's built-in distribution. So you can just start up an airline node on each of the 400 computers, and then you can let them talk together.
It's scalable.
Yeah, then it's scalable. So, and that's how it is today. And then maybe 10 years from now, when memory is even cheaper, right? You don't only need maybe 10 computers connected, and it could actually have the power needed in memory storage to actually run this.
Right. Can I jump in and suggest 7-minute break because Doug, you are next. So we can.
That was sort of a pre-question, but I had one other question. If nobody else has another question, I can defer mine until my talk.
We need a small break, so if you bring it in your lecture, after your lecture, we will have more free.
Okay, so you're going to take a break now. Okay, that's fine.
We are taking break now.
Yeah.
Okay.
So thank you very much.
Congratulations, good job.
So should we
Stop recording.
Yeah, and I have to find out where that is.
That's the one right at the end.
That more. That one?
Yeah. So,
Stop recording.
yeah.
Yes.
Yeah.
Recording stopped.
You have a discrete chunk.
Perfect.
Good.
Rich is my corner. Could you stay there for a second?
Yes.
I'm a vagrant from the computer industry, and I'm a non-believer in the old AI.
Yeah.
I wish you luck with the new AI.
Thank you.
There is a way of thinking about what's going on with neural networks, and as you know, it develops a series of things which we do not understand.
Yeah.
But it is possible. This is a wild guess by some people I know, that the language is sort of encoded in a way which the engine is not able to describe. But there's some possibility, if you heard of the two talks by Peter Rowlands and the talk by John Williamson, they're in a sense describing languages to grasp all of these features of reality. And perhaps even more relevant is what the lady who spoke, Nicola, about Sanskrit and the fundamentals, so going that way back. And then finally, also in ANPA, is Grenville, who's looking at stuff deeply to do with the binary level, right? Now, in the philosophical world, there's an idea that way back, I'm talking about 20 or 30,000 years ago, people used to communicate mind to mind. And that the organic mind is storing copies of what is thought in another space. So all of these things are relevant, but I think the fundamental idea is that the actual computer architecture is absolutely hopeless looking at the massively parallelness, and the other thing is it's essentially not an organic thing, it's essentially a machine.
So, that's right. Thank you.
Thanks very much.
So I'll take a break.
Would we be 400 computers wired up next door in physics or more than 400?
Yeah.
So we're doing particle physics calculations. So basically nothing, no big deal.
No, and the amount of RAM we have, but a high-end, racing computer can easily have.
Hey.
Right. And if you pay a little bit more.
Hey, Ehrlich, if you can unshare your screen, I can share mine.
Yeah, you're welcome.
Yeah, but you have to unshare your screen before I can share mine.
Yeah, he needs to do his.
I will stop share one morning.
So you stop your talk as well.
I have.
Yeah, start it again but in a few minutes.
Thank you.
So not immediately, otherwise we'll just record casual chat. Yeah, thank you.
So And
I think the world is ready without playing computers. Thank you, Mr. Watson.
yeah, but 10 years from now, what I have, it will simulate on a laptop basically what happens in the brain, I think, in returns of needed like power and memory. Yeah,
Start thinking things out.
yeah. So that's what I'm.
Will this bloody thing ever develop a consciousness?
If you want to talk, Doug, I'm sitting here in my home in Switzerland without anybody to chat to.
System that's reacting to the whole world, and
You're muted, right?
it makes its own decision. Then it will actually end up being conscious.
You think so?
Yeah.
I think, it's the interaction between us and the universe. The zero between us.
Who's this, Andrew?
Definitely common ordinary.
Sorry?
Who's speaking?
I'm speaking. My name's Mike Horner.
Mike Horner, yeah, right, okay.
Hi. We met before.
Yeah, exactly.
Did you hear the comments Ulrich made to do with AI?
That's much more
Yeah, well, I'll comment on that.
Okay.
And so those systems machine are automatically build all those patterns automatically, just like the brains are building patterns by what we're seeing. All the pattern will be there.
Have you come across the idea
Not the same
about brain
nature has
as opposed to mind? There's a woman who's a philosopher and also a thinker about movement, and she argues that when plants and then animals tried to move, they needed to have a model of themselves and a model of their external reality, so that the brain in that sense is just a sort of real-time model, so you don't bump into yourself or the things around you.
Oh, yeah.
She's part of the whole business of biosemiotics, which for some bizarre reason is very seldom discussed. But I was struck with that. If you're interested, I can send you the reference.
Yeah. Also, Mike, where are you in Switzerland?
I'm living near to Geneva, but just 10 miles up the road.
Okay, in 2 weeks I'll be in Zurich.
Oh, yeah? Are you giving a talk there or just on holiday?
My daughter lives there.
Oh, yeah?
That thing about corn.
So yeah, we'll just connect up after.
It's amazing. Yeah, I still.
Are you?
Especially if you worked with Mike for a long time. So.
Yeah, I worked with him in the 80s and early 90s.
Yeah.
And in fact, I was very taken with his philosophical comments. I wasn't so interested in the coding and stuff like that.
Yeah.
But these points that Ulrich made about parallel computing, they're very active in the high.
Yeah, I'll reinforce some of that. Yeah, I might talk.
I mean, there are, as you know, there are people making memories with processors in each cell and stuff like that, which of course raises a whole weird question about how can you program such things. And it starts to be a business on its own.
Mm-hmm.
Are you ready to start?
I was always hoping that Mike's work would be taken up by other people.
Very good.
Right. Well, essentially I have taken it up, so.
Yeah.
Right, that we are about to start.
I'll turn off your phone, please.
Yeah.
That's Doc's outline. Sharing the screen already. Don't do anything.
Okay.
Just record screen.
Okay.
Just start recording.
Yeah, when you guys are ready to start, just record and I will.
Recording in progress.
Okay.
Okay.
Yeah.
Okay, you all can hear me?
I can hear you.
Hear you, Doug, and we are ready to start. Forgive us slowness, but I mean, with every degree centigrade up, we are getting slower and slower.
Yeah.
Yeah.
It's a little bit like a greenhouse in here, so if we behave strangely, Doc, that's what's happening.
Oh, okay.
So,
I'll send you cool thoughts.
Yeah, please start.
Yep.
Okay, so if you guys are ready, I'm ready. So I'll start whenever you give me the go.
Okay, guys,
Yeah.
let's start. Hey, guys, we're gonna wait up. Let's vote. Yeah, Zach's gonna fill us in.
Okay.
Yeah.
I have the authorization to go. Yes.
Yeah.
Okay. Here I go. Hey, welcome everybody. Hey, thanks for allowing me to speak here about Mike's and I work, and I'll keep to the time limit because I know you're saying that space has to be empty in an hour. So this is a retrospective summary of what we did, including the geometric algebra. Some of these stuff you've seen 2 years ago when I presented, and so I'll go through those quickly, but it's a good summary talk. So I'll focus. So Mike and I didn't always agree on things. I was interested more in the quantum mining perspective. So I was interested in quantum computing since my PhD was in quantum computing, and Mike helped me with that. So but the commonality is this geometric algebra approach that he introduced to me, which includes the Bitcoin demo. And then this top talk was a separate talk. So here's when I first met Mike, was in the conference 92 and 94 conferences. By the way, there's a link to a secret page that has all the, I don't post that anywhere, but here you can go to those links, and just because supposedly it's copyrighted by the Computer Society, but one day they opened all their stuff up, and so I just downloaded all the repositories and stored them on my site so people could get at them. So Mike started working with me after this for PhD in 97. I went and visited him in Crestone when he was first building, essentially camping out in his place while he was building it, and for a week. And this is when the GALG tool emerged, because we were trying to do these computations by hand and we couldn't do it. We kept making sign errors, and then the whole result would be void. So by 2001, I defended my PhD topic, and Mike was there for that. And then I graduated, and the first program was in Perl for this GALG tool. And then I attended the conference in the fall and presented that work. And all of these things are on my website, quantumdoug.com. So you can go there and see the ANPA section, and you can see all this stuff there. So finally, I built a new version of the Python version of the interactive tool instead of Perl, so that it was more interactive. It's only about 2,000 lines of code. It's not big. And I think Mike was my only one customer worldwide that was using my tool, really popular tool. But then in 2012, Mike says, Doug, help me with this. I think I have a standard model. So Mike was interested in Topsy, but he was also interested in quantum computing. But since that's why he worked with me for my PhD, was that. And we showed for my PhD that you can show that you can build a qubit and an e-bit using just pure bit vectors from geometric algebra, and you can bootstrap physics that way. So at least qubits. And so then he says, well, here's the standard model, and he thinks this was the Higgs boson. So we did this paper, and I gave a talk about that on pervasive entanglement in 2013, because it turns out when Mike was wanting me to do that, I hurt my back. So I was on painkillers during that time, and I was helping him with coding and models and testing. But what we realized is that his model for the standard model seemed to hold water. And it says you can bootstrap not only qubits and e-bits, but you can also bootstrap the entire standard model using the Higgs boson. And that was that talk that I gave, the pervasive entanglement talk. And so you can find that on my website too. And so finally, of all of this, I released, and Mike didn't understand when he says, this is the Higgs boson. I says, well, Mike, that's entangled. See, he wasn't used to looking at geometric algebra the way I was, and I knew what entangled states looked like, the Bell states, essentially. So that was the real aha phenomena when we started working on that part. And so finally, I put all this in my book in 2019. I released it. I started working on 2014, and my co-author was Bill Tiller, who's now deceased, but he's famous for working in metaphysics area, and I'm the only person that he's ever co-wrote a book with. He's written a lot of other books, but he had an assistant. But this is it. And so then I gave these talks, and then Mike passed away. So here's the big picture. Everybody's looking at physics, And again, some of these slides were in some of my other talks, so I'm going to kind of go through this quickly because I have too many slides for the time. But realize that there's this point here below the, you go down to the Planck scale, and then you go down to where there is no space and there is no time. This is the area that Mike and I were working. We didn't believe that the geometric algebra system itself was in space-time, which is completely opposite of what the standard model stuff is, and even quantum computing. They all put everything assuming it's in space-time. And so we're trying to do sort of more fundamental. It's a hyperspace with an infinite number of orthogonal dimensions. And this picture down here is trying to represent what that means. But remember, every pair that you pick is orthogonal to all other pairs. And you can't compress that and put it in a three-dimensional space. It's a superspace, hyperspace, that has all these orthogonal dimensions. And then if you take two of those combined, you get more dimensions, which is the orthogonal Vic vector, and then you combine those qubits. And so this was all happening in what I call protophysics, and it comes from bootstrapping bits, qubits, and e-bits, and this is all pre-space and pre-time. Okay, so this is
we are losing you, Doug.
Completely fundamentally different than anything else in physics it's doing, and this is really Mike's work. So, say that again.
We lost you.
Can you all hear me? Okay, so my internet keeps dropping out a little bit. Yeah, so hopefully you can see it. Okay, so you can see me now. Yes.
Yes.
Okay, great. I'll just check with you every so often to make sure that everybody's online. So this is a kind of way to think about this. If you have A and B as bit vectors, Mike would call those tokens, or he would call them places in his computer model, in his block world model, spaces for that. But I don't look at. I wasn't interested in Mike's I mean, I knew since early 2000s that he had Topsy, but I wasn't interested in that. I was interested in these more primitive notions of bit vectors, okay? And so you can think of each A and B as a bit vector orthogonal to everything else. And if this is the coin demo here, we're going to talk about it. If you have A plus B, that means it's concurrent. This is what he calls co-occurrence. It's that these two things happen at the same time. Well, this is not a relativistic co-occurrence. This is an exact. And physics doesn't really have anything like that in you can't have simultaneity anywhere in physics. There is no simultaneity in relativity. But this has to be truly simultaneous. Otherwise, you really don't have it. So we would call this a space-like plus operator. And then if you have co-exclusion, it says, I saw this state and later I saw this state. Well, that means these states here are the inverse of each other. That means some algorithm, some operator fired this and turned it into this. These can't occur simultaneously. They're mutual. They disallow each other. If you add these two sides up, you get 0. Okay, and so if you add those two sides up, it means it cannot occur. So Mike had this notion of cannot occur in his So this is a co-exclusion. It says if I saw this state, later I saw this state. So this is a sense of time-like in the sense there's a change, but it's abstract time. It's not actual time. It's not relativistic time. It's not. There's no seconds to it. It just says a change occurred. So these two pieces here are actually more primitive than space-time. And in fact, if you don't have these as a primitive, you can't simulate this with anything else. So this is fundamental. And if you guys don't understand that, then I haven't done a good enough job or spent enough time talking about it. So if somebody else wants to follow up with me on this, this is really important. And so this built-in concurrency and change, there's no light cone yet at all. So it's all in space-like computation environment. And by the way, entanglement is space-like. The same thing is if you don't have a space-like primitive in your representation, you can't simulate entanglement unless you have a space-like operator. So entanglement is part of this primitive nature, and we'll see where that comes from too. So just realize these are fundamental because you can't simulate these in any other kind of system. They have to be fundamental. So you've seen the coin demo here. I'm going to just show that briefly here for the purposes of looking at this. but basically how many coins do I have? Well, if you show them both simultaneously, truly simultaneously, and that is resolved, and where did the information come from the presence of the two coins? So this is the co-occurrence again. And this is, he calls this non-Shannon space-like information derived from true simultaneity. I believe if you took two dimensions and you said in the Big Bang, all of a sudden we said two dimensions are all of a sudden coming together, this has an effective energy of this co-occurrence of these two dimensions coming together, and it forms a qubit. Well, that bit represents an effective energy by Landauer's principle. So you could say, well, that bit, the bits coming together in dimensions coalescing into these qubits and e-bits, and 2 and 3 combination pairs of these is how the Big Bang occurred, and I call it a bit bang. It's how you can create matter, energy, space, and time from nothing, and the nothing is just bits. So you don't have to figure out, oh, and even space and time emerges from this. So this is a big idea here, but so far nobody's talking to me about this, and so I'd like someone to think that this is really important, like Mike and I felt that way. So what is the geometric algebra then? Essentially you have G0 through G5, 4 through 5, you have different sizes, just like Hilbert spaces of different sizes. And the difference is that you have a single vector A, or you have A and B, these are orthogonal, A, B, and C, and then, but the thing you have, key is you have these, we call spinners. So if you have dimension A and B, and you take the outer product of them, all you can do, since they're orthogonal, is create a new thing called a bivector, which is this planar view. It's actually a two-dimensional object, and I represent it like this, and that has an orientation in and out of the page, and this is a spinner. By the way, Hilbert space doesn't have this concept. They have something they call I, but that's slightly different, because here this is primitive. It's saying how you can create, in fact, here's how you can create I. If you take a spinner and it's equal to its inverse, it's anti-commutative. So if you take the square of it and you insert it in here and you solve it, you find out that any vector is the square root of -1. So you can even bootstrap, not only can you bootstrap bivectors, which Hilbert space doesn't have, you can bootstrap spinners, the imaginary numbers from this, and that's why you can represent a qubit in here, even though you have just pure bits as the primitives. So you have a geometric product, which is equivalent to the tensor product, but the difference is that in tensor product, all you create is more vectors. So you have no structure to the space except for more dimensions. But geometric algebra actually has these topological things called bivectors and trivectors and n-vectors, and those things are the basis for not only topsy, but it's also, we believe, the basis for the structure of the standard model. Without these things, it's just a high-dimensional space, but it doesn't have any structure to it. It has states, but it doesn't have any structure to the states. So, and this implies if you see A minus B, and then later you say minus A plus B, then you know that at I equals 0, that means there implies AB. So if you see any states like this, and you see these states have changed, it implies operators to haven't got there. So that's how co-occurrence and co-exclusion are defined. And so you can take a truth table and you can turn this into like, and I'm going to show this in the next slide here, so I'll just go to that. So here's my geometric algebra tool. It's in Python. Anybody can download this. I can give them the link, or it's in the last talk I gave. If you have A plus B, A is in Python is a variable bound to a vector A. So it prints itself as a vector. So it's a redeval print loop that prints itself, self-printing and we use operator overload for plus so if I take B outer product A, puts it in standard normal form, and it takes, the standard normal form of B outer product A is this bivector called A outer product B that's inverted. And likewise, we can take trivectors, the same thing, and you can create the smallest vector state for any time you have A plus B plus C. By definition, you have all of these bivectors and trivectors as well. And if you were to look at what this means in a truth table, it looks like the state 0, 0, 0, 0, 0 plus. So that means this looks like a truth table, and I'll show you in a minute what that looks like. But then we can represent qubits and a spinner object and change it so that we can get the square root of a spinner, and we can take superposition And we can get quantum registers, where the quantum register, instead of using the tensor product, we use the geometric product to get the state. This looks exactly like the Hilbert space representation for a qubit, but it's in geometric algebra. Okay, and then here's the truth table. If you take something like this, you can put it in this function we call GA states. And what it does is it iterates through all the combinations of A and B with plus and minuses. And then what it does is it shows you what the output of this expression using this algebra, this essentially addition and multiplication rules. Okay, and I did all this stuff, by the way, in my PhD, which I graduated in 2002 with that. But you can also go in and say, you can also look at what those bits are, and we can look at what the bit rate is. Essentially, if there's these bits, you could say, out of all the possible combinations of A and B, how often does this state occur? And we can assign a bit value to that, and that's where we can show that the coin demo comes out of qubits in geometric algebra. So we can actually show that. So what are these again? Here's the one-dimensional bit. There's three orientations. We think of them as truly as vectors. And if you have the same bit A and minus A at the same time and you add them together, you get 0, and that means that those two states are mutually exclusive and they can't occur simultaneously. That's what the 0 means, cannot occur. And these, I call these bit vectors, but they're also proto-dimensions and they're also distinctions. So they're also kind of like laws of forms kind of distinctions as well. So when you have two of these, now you have two orthogonal dimensions, and this looks like a qubit. But this looks just like a qubit. This is a Bra-Ket notation, and this is an orthogonal Ket 0 and Ket 1. These are equivalent to state 0 and state 1. And if you represent that graphically, it looks like that. And by the way, when you do the analysis on this, you get actually qubits, but you actually see unitary expressions in this algebra. You can go through all the expressions in the algebra. You can find things where the square is 1 or the square is 0. Nilpotent and idempotent I'm getting the name wrong here, but neutrinos are where their square is 1. Okay, I'll talk about that in a minute. So once you have three of these, then you get trivectors. And by the way, if you have a three-dimensional space, then you can take multiply A to plus B times plus C times ABC, and you get this thing, which is the quaternions. And we showed all of this in the previous things, and you get quarks. And this is what Mike showed 10 years ago when he says, Doug helped me, says photons, we can get gluons, we can get quarks, we can get mesons, electrons, and neutrinos, and you get protons and neutrons as well in there. So this, you could completely identify every state in a three-dimensional space, and guess what? There's no room for E-bits. The only way you can get an E-bit is if you take two qubits, so now you have a four-dimensional space. You can find this Bell operator, which is just the spinner of these two, and you can apply these operators to the quantum register state, all using geometric algebra, and you can get this state, which is the Bell state and the magic state. And these states are all entangled, okay? And what we find out is those states are entangled because it's using multiplicative cancellation in geometric algebra. So, you can show how you can these entangled states. If you take the Bell operator and you multiply it times a quantum register in states A0 and B0, you end up with these states, the spinner of 00, spinner of 001, 11, and that's just, these are the actual Bell states. They're exactly equivalent to the Bell states in geometric algebra, and they have exactly the same properties. And what you find out is this state here is actually like a qubit in a higher dimensional space, and you can use a single operator for the spinner to rotate through all the states for a qubit. By having a SA plus SAB, you can apply this Bell operator over and over and over again, and it looks like a phase angle in this higher dimensional space, and those are all of the quantum space. So an E-bit is actually a qubit in a higher dimensional space, and it requires you a four-dimensional space to support the differentiation of that and to support the multiplicative cancellation. So the thing is, and why is this, this is true? Because you can't factor this. This is inseparable, what's called inseparable. And these Bell and magic operators are irreversible, and I've proved that in my dissertation 2 ways. It's irreversible in G4, and that's completely different than we see in Hilbert space. So I would like somebody to help me figure out, well, how important is that? I believe it's very important. See the proof that this does not exist, and I did this exhaustively by searching all 43 million states and ran over a month to run this proof exhaustively, and then I did it closed form too, and that's all in my dissertation. So if you can look at every possible state, corner state in the space, and you say, well, there's no possible operator that is equivalent to this, then this is irreversible. And again, we proved that. So, and the reason why this works is because if you have a qubit, you have state A0 and B0. These are the 2 notations I use for qubits. Capital A, which stands for qubit A, capital B for qubit B. If you multiply those together, implied multiplication here, then you get this state, which is the same as the, but if you look at the underline, this state here is B3 and this state here is M3. So a qubit state actually has Bell and magic states concurrently together. If you multiply any qubit state that has this representation times either the Bell or magic operator, then the conjugate of it cancels out due to multiplicative cancellation. So if you multiply this, one of these pairs disappear, and that's erasure of information. Landauer's principle says this is irreversible. So again, multiplicative cancellation, irreversibility, it means that it's irreversible by 3 different arguments here. This is an important argument. Someone in ANPA should realize how important this is and help get the word out about this. And I don't know if that's possible for this group, but I would encourage somebody to talk to me about that. This is one of the big things that Mike and I figured out during my dissertation, and then we figured out additional things. Mike figured out that there's a thing called a Tauquirnian. Just like an E-bit is a higher dimensional version of a qubit, Mike came up with this term called Tauquirnians, and he called them T sub I, J sub I, and K sub I, and they're equivalent to quaternions, I, J, and K. It's a higher dimensional version, right? And so instead of having a single bivector here, it's the sum of bivectors, right? And these states here act like a higher dimensional version of a quaternion, so they're a Tauquirnian, it's a quaternium isomorph. And you can say, you can take the conjugate of those, and those also exist. And they're anticommutative. You can take any one of those. You can prove this easily. And you can sum all these together, and you get 1 plus ABC. And you go, well, what is that, Doug? Well, it turns out it's equivalent to a sparse version of -1. So, and that squared is equal to +1, a sparse version of +1. Okay? And if you take a look at this report I have that says, what are the states of this 1 minus ABCD, which is a 4 vector that is a combination of all the states of all the vectors in a 4-dimensional space, then you see that this is a sparse version of -1. See the minuses there? And the other versions are 0, so which means they do not exist. And likewise, if you take this one, -1 minus ABCD, you get the plus version of it. So all of these things show that it's equivalent to a quaternion with this caveat that it's embedded in a higher dimensional space. Okay, and you can show that this is exactly equivalent to quaternions, and that here's all the Bell and magic states for this. So, so one of the things that Mike realized was if you take all of these Tauquirnians and you sum them together, you find that there are cases where H squared is equal to 0, which means it's a boson. Okay, and he believes that there are all these characterizations here of this. But by the way, you can take this. This is, by the way, just the complete even subalgebra of G4. That's all it is. And you'd think that would be a special thing. Well, it is. We think it's the Higgs boson. And so, it forms. You can factor that because it's just the even subalgebra, and you can factor that out, and you get this. And so you can, since all factorizations are valid for geometric algebra, because you don't know which factorization it's using, it looks like time-like thing with space. This here we think is a quaternion. It's also nilpotent. AB plus AC plus BC is nilpotent. Its square is 0, which means it's like a photon. So I think space itself is like a photon. In fact, this is a rotation of a photon. If you take A plus B plus C, which we think is the photon, it's nilpotent, its square is that. If you multiply A plus B plus C times ABC, you get this. So if something is a factor is nilpotent, then this is also nilpotent. Also, you can convert it to this, light and space. So here you have space again, plus light. So here's light. So you can, again, Mike was really good at finding these various factorizations. And what you can find that there's 16 permutations of this here, that where x squared is equal to 0, and then you have a bunch of them where this is true, where you can rotate. This is a particular state where it's anti-commutative. You can put it in either order and you get the result back. Okay, and then there's another 48 states where this is where the square is equal to plus or minus ABCD, and he thinks this is the Higgs, and this is kind of like a mass-like primitive because its square is ABCD, and it has this property here. So these again important concepts because it's complete even. He calls this a protomass. This is what Mike called this. Okay, so what does this mean? So here's the normal standard model. Okay, and this normal standard model is they just put it in a matrix like this. Okay, square matrix, and then all of a sudden they put the Higgs on the side like this. Well, we think it should be organized like this. In G1, there's only 9 states. It's a bit. It's just the bit and an integer. That's it. So, and then in G2, there's 81 states. Well, you can see that there are neutrinos in here, and we think that there is a new neutrino we call the X neutrino, and I'll talk about that in a minute. But there's also 2 bosons. So we think the Z and W bosons are actually 2-dimensional, and we think the neutrinos are 2-dimensional, and we believe that there's a 4th one because if you look at all the permutations in this space, you find out that there's a 4th state. And you go, and one of the other talks I've given, I said, if you take this neutrino, what is it? Well, if you take the sum, for every neutrino, there's an antineutrino. So if you were to take the sum of the 3 antineutrinos and sum them up, you would get this neutrino. So even if we could create an experiment to produce this device, it would be very hard because you would have to sum the 3 antineutrinos to get this neutrino. Probably doesn't occur very easily in nature. So, or even if they did, neutrinos are so hard to measure you couldn't ever see it. So that's what we believe, that there's a prediction here that there's the thing. Also, we believe that here's the quarks. There are 3. You have to have 3 dimensions to be quarks. You can't have quarks in 2 dimensions. There's not enough room in the spaceport. So you find the gluons and you find this photon, but you also find what we thought maybe this is the quaternion. This is like the X boson that they're talking about. It's a low energy boson. It's essentially a rotation of the photon, you know, and so this how space and light are tied together. Okay, and there's electrons, but we find that there's twice as many electrons as we have, because for every one of these electron states, there's the anti-electrons versions of these too, the antiparticle versions of these. Well, we see 12 instead of 6. And so what we're seeing is the chirality version of these electrons in here too. But then when you do that, all of the states are completely comprehended in 3 dimensions. So once you get to 4 dimensions, now we think that there's the Higgs boson is in the 4-dimensional space, and there's about 17 other particles and 30 other bosons in this state, and we haven't explored completely what all that was. So and that's because if you have unitary and nilpotent and things like that, we believe that those are how you find particles in these spaces. Okay, so here's this about how you bootstrap the universe. You start with space. You just starts with 1-dimensional bits. Okay, and that's equivalent. And as you increase complexity, now two of those co-occur. So now you have qubits. So if you did that, you can look at the distribution of a 2-bit space, and you find that there's a probability that there's going to be qubits in there probability there's going to be neutrinos in there, probability there's going to be W and Z, just because the space has those probabilities in there. So once you have that's equivalent to 2.17 bits by just looking at all the permutations of that space and saying how often they occur for qubits. So then finally you get to a three-dimensional space, and all of a sudden photons and mesons and all this other stuff starts appearing, quaternions. And so now you actually have space. And then you have Tauquirnians, and so you can bootstrap the universe completely from bits by just co-occurring more and more bits into bivectors and trivectors and quad vectors and like this. And so you could bootstrap the universe from nothing. You don't have to have space, you don't have to have time, you don't have to have matter, you don't have to have energy. All you have to have bits and co-occurrence, and that's it, period. And you can bootstrap the universe, okay? And then you can also do Tauquirnians, where you can get space-time emerges probably in G5. And then there's also there's also our version of neural networks that I called correlathms. And essentially this is a high-dimensional neural network space. This is the space that Hawkins is using in his company, in the neural computing company that he's doing. And he basically has gone on record, says, if you're not using Canova-style memories, this is a generalization of Canova-style memories, it just doesn't use phase angles, it uses distance metric as a distance metric. If you're not using this, you're not doing AI. And the reason is because there's mathematical properties of this space that don't exist in lower dimensional spaces. So if you get sidetracked by Hawking's, oh, he's a neural computing guy. No, there's this math behind the neural computing that he's doing that is more fundamental than any neural model you're doing, which is the same problem I had with Mike's work too, is he was so focused in on the neural computing. I don't believe the brain is a neural computer. I believe the mind is a mathematical hyperspace mind, quantum mind, and that the brain is just a three-dimensional antenna that converts a hyperdimensional space into a three-dimensional space. So Mike and I completely disagreed about that. And so I never worked on Topsy, partly because his early version of it stopped working one time, somebody broke it. And so then I suggested to Mike 10 years ago that he do it in Erlang, because Erlang has the massive parallelism that you need to support what he's trying to do. So I think then that's why Erlang work was done by Ulrich. Okay, so here, what was the result of what we did? We had this hyperdimensional